a write-up of what I'm going to talk about, and then below that, much more detailed write-up of the code. And there's a fun SVG in there, but I could also share screen to be able to scrub the SVG and talk about the different parts. But yeah, so please at any point interrupt me for questions also.
Okay, we'll do.
So our approach to hole punching, I believe, is a little inverted to the libp2p approach, in that we took a look at Tailscale as our primary inspiration, and we actually implemented some of their protocols in Rust to use as like our hole punching strategies. So we basically, the API ends up being, there is a magic socket that we plug into a quick endpoint, because we do all of our communication in quick. In Tailscale, it's WireGuard, and for us, it's quick. And so we plug in a magic socket into a quick endpoint, and the all of the hole punching and all of the decision making about hole punching happens inside that magic socket. So we basically have hacked a UDP socket and are intercepting communication there and doing all the hole punching and routing of packets inside there. So what that ends up kind of looking like when you start a magic socket, you first do all of the like magic of figuring out all of the information about your interfaces, your network interfaces. Then you do like a net, we call it a net check report, where you send out probes to stun servers and find out all about yourself. We do hairpinning checks, we do captive portal checks and port mapping. Once we gather all that information, there's a separate section, a separate sort of thing that we've got inspiration from Tailscale from, which is these derp servers. So we have these servers that do all the packet relaying, encrypted packet relaying, and also, so not only do those coordinate the actual hole punching when we get to that step, but they're also our fallback servers that can relay any data that isn't able to, if we're not able to make a direct hole punch, we can relay everything over the derp server. What we really liked about that approach, although there are pros and cons, we liked about that approach is that you're almost like guaranteed to have a connection, unless there's some crazy corporate firewall stuff happening, because that just happens over HTTPS. So there's a lot less weird UDP network, NAT like and firewall disruption from that. So we know we almost always have this guarantee that, all right, the data is going to get across to the other peer that you're trying to connect to. The downside of that,
so
obviously,
the
is
packets
that
encapsulated in the HTTP.
Yeah, so the way it works, and there is some streamlining of this that we can do, but currently what ends up happening is you have your quick packet, and it is encrypted, the quick encrypted packet, and you send it to into your magic socket. Magic socket then looks at, oh hey, who are you trying to talk to? It sees, do we have endpoints for valid endpoints for that peer? If it has valid UDP endpoints, and in this case, valid means that we've gotten a pong back from a ping on that UDP endpoint, and it hasn't been longer than, I don't know, say a minute. If it has a valid endpoint, it will just send it using the UDP socket, send the quick packet off using the UDP socket. However, if it's invalid in some way, or we don't have one, we just have a public key, then we start communication over these derp server relays. And then when we realize, or when we come to that point of decision and we see, hey, we don't have a valid UDP address for this peer, we then trigger the hole punching. And that happens using the Tailscale calls it the disco protocol, which is a very fun name because it's like you're doing this discovery dance. So you send a call me maybe packet over the derp server.
Mhm.
And while you do that, you also send disco pings to any address that you have for that peer. If you don't have any address for that peer, you just send the disco message. And I'm sorry, you just send the call me maybe message, which includes a list of all of your addresses that you think you can be reached on. When it gets
Got
to the
it.
other side, that peer can either ignore your packet, ignore the call for call me maybe, or it can
Mhm.
send one back and also send a ping to all of your known addresses. So hopefully you know some of their addresses, they know some of yours, and that is how the hole punching happens. If it doesn't happen on that round, however, they've sent a call me maybe message to you with all of their public addresses or their known addresses. So now you both have your address book filled, and maybe on the next try, the next time you send a packet, you're able to actually hole punch. So that's the
How many packets you send per
dance.
address?
One ping per address, one ping
Okay.
per known address. And I think that's true. I could double check that, but I think right now it's one ping per address. And yeah, so that's the
The ping is just
dance that
like a
happens.
UDP packet that is just like, well, what is a ping?
Yeah, so it's either it's just a UDP packet. It's encrypted. There's the disco protocol is an encrypted protocol, so you need, that's why you, in our world, you need the public key of the person you're trying to communicate with so that you can do the like cha-cha box encryption. That was a fun, interesting, so Tailscale and WireGuard, which we've done a lot of our referencing from, doesn't have the restriction of we want to dial via peer ID. We don't want to necessarily dial from just an address. We want to be able to dial from peer ID. So there's actually a fun, it's a weird little dance that you do. You end up having to, and because you have to spoof, we basically spoof the quick endpoint. So we need to have a unified address that all peer communication seems to be coming from and seems to be going to.
Mhm.
So there's a weird spoofing that we do where when you want to dial a peer, you specifically have to the magic socket, add that peer explicitly with the peer ID. And whatever, if you know any addresses, you add those as well. And you get a address that is the like quick spoof address. And when you want to talk to that peer, that's what you have to give quick, because you have to have some relation between some address that quick is trying to dial and the the peer ID, because quick doesn't speak peer IDs. There's no way to ask it to dial the peer ID. So we have to like do a hack where we make that relation inside of the magic socket.
Oh,
And then
interesting.
any
So like
communication. No, go on.
when you dial a peer, you're actually like using a fake IP address in
Yeah.
tuple, and this maps in some table to like a list of possible addresses.
Yep.
And then let me just make sure I got this. If you don't actually have a real connection to the real addresses, you'll do this relay over derp. Is that
Yeah,
correct?
which understands public peer IDs. And then hopefully, so the derp networking is its own little fun thing where, hopefully you're connected to the same, you end up having like a home derp server, which is the one that you would advertise, hey, this is where I usually live. Like this is the one that I usually connect to. And if someone's trying to contact you, they would either need to be connected to that derp server or a derp server in that region. So each region is just a mesh network of derp servers. Everyone's just one hop away from each other. And the derp servers will relay the packets through that mesh network to the person you're trying to communicate to. So that does require this whole, like all the hole punching magic does require that you are connected to a derp server. And if you're being smart about it, you are trying to connect to the derp server. You're trying to connect to the derp server that the person that you're talking to is connected to as well. And if not that, then at least one in that region. That all would happen as configuration or some additional information you have to pass down. That's not part of the like hole punching dance. We just take whatever information that you've out of band somehow figured out that this person is connected to this derp region. And you have to add that derp region as, hey, this person is likely here, so that when you go to do the hole punching, you're talking to the right server.
Yeah, okay, that makes sense. Here's a question. So let's say you start the hole punching and you're relaying communication over the derp and you have a successful hole punch, right? So now you know that there's this path, direct path.
Yep.
Do you like just start sending the quick packets over the direct path instead of the derp?
Yeah,
Okay,
so
cool. So you have like, go ahead.
Every time you go to send a packet or a group of transmits, as Quinn calls it, so they do their own bundling, and they'll try to send a group of transmits at once. Every time you go to send some quick packet over, you end up, you have that that spoof address that I was talking about. At the moment when you go to actually send something to that address, we do that mapping, sorry, not mapping, well, no, a mapping. We look up that address, we see who that's actually for, their peer ID, and we have that list of potential addresses. So that list of potential addresses, when you go to do the ping-ponging of the hole punching dance, when we receive a pong back, you update the latency of all of those addresses. And so you have a latency and you have an expiration time of how long you're going to decide that that's valid for. And if you have, when you go to do that, hey, give me the best address for this peer, I want to send these packets to this peer, give me the best address, you compare all those latencies. And if there's one that's good, you just send it over that UDP address. If there's not one that's good, you do the, maybe do the hole punching dance. But if it's also, it's not necessarily a good, if you don't necessarily have a good address, for example, one has a latency that we don't like. So we know we have proof that we've communicated on this address, but we don't like the latency. We might also say, hey, also send this packet over the derp relay. Or if there is no address, of course, we're sending it over the relay. Or if we've never had any latency, information, so we've got no pongs back, we will pick a UDP address to send on and like cross your fingers, but also always send just in case, and then also always send over the derp packet. So and then that happens every time you go to send a packet. So the moment we get a pong back that says, no, we have a latency for this, it switches to the direct connection. I can like scrub through the SVG and we can like talk about the different moments, if that's helpful.
That sounds good. I think you should be able to share your screen. So I guess I have a couple questions.
Yeah, please.
Is there a spot where you're like changing the UDP headers before sending the packet out?
You mean like
actually that question's kind of boring. Let me change it. Let me give you a different question. I feel like I can kind of reason this one out. But I guess like one thing that's kind of surprising to me is it seems like you're doing a lot of things that Quick does out of the box, but like on another layer, right? So like Quick has like data path validation, it has like connection migration. And I don't think there's like, I'm pretty sure there isn't like a well-defined way of like using these to hole punch. But yeah, I guess like what was the reason for like,
yeah, totally. So I'm just flat out, there are a ton of things that we could research to better leverage the stuff that Quick already has. There's also some pieces that we know of already. I know this is tangential to the question that you had, but for example, if we get an incoming message and that first message isn't a disco message, which is the hole punching ping pong thing, because those are encrypted with the public key, because they come with, hey, this is my public key from the remote. We are able to then relate that address to a peer, right? If the first message we get from them is just a UDP packet or some quick packet, we don't necessarily, if it's something is a UDP packet, we don't necessarily have that information. However, we use self-certified, our quick connections are the libp2p TLS self-certified with certificates. We could probably get the peer ID, or we have to research into, hey, is it possible for us to pull that peer ID out of those certificates? And so we're not worried. Yep. So anytime we get a quick connection, as soon as that happens, we have an identity for that peer. We're not doing that right now. We definitely could. So there's definitely, there are things about this that need more research, and we're going to be working on leveraging this for a while. So yes, the answer is yes. The thing is, because a lot of the base thought structure came out of this Tailscale implementation, they just have a different, they're on WireGuard, they have a different relationship to the underlying protocol that's happening, or not underlying protocol, but you know what I mean, the negotiation of the stream than we do. So there's just a lot to explore and make better. Does that answer anything of yours?
That answers a bit. I guess like my high level question was like, there's a lot of like building blocks Quick gives you here, and it seems like you're re-implementing those. But your answer seems like, yes, a lot of this is because of like I guess the historical context of coming from Tailscale, rather than like thinking from Quick to start, and like not opposed to using more Quick building blocks.
Yeah, absolutely. So, I mean, you guys know this shit is weird and hard. Like hole punching is weird. A lot of the focus for this first push was we need to do a big push to get it working. And then like the rest of the push for the rest of our lives is to make it better. Like,
have you heard of the mask protocol, MASQUE?
I haven't looked into it though.
Okay, it might be interesting for you guys also because it could replace this derp component, and it's basically how you do quick. It's like an RFC on how you do like quick proxying. It does like basically what you're doing. The one difference here, and you probably don't use the proxy enough for this to matter, and I'm curious if you guys have thought about this, but like stacking congestion controllers, is generally like a little scary and not great.
Yeah, we've already sort of run into that. And there were improvements made, but there's a lot of weirdness around, like you said, the congestion controller dance, I guess I'll call it. So I think that might have been the context in which I had heard about mask, actually. Now that you mentioned the congestion controller, but yeah, okay. So do you want to, should I share screen?
This is my favorite part. So please share your screen.
Okay, and I can can you guys see this SVG that's happening here? All right, I'm gonna minimize this so I can, okay. So just to give some context here, we have two NATs, they're mislabeled. This ends up, the get NAT here is actually the NAT for the serve side, and So this is the serve side NAT and this is the get side NAT. And then this is our
What do you
derper
mean
that's
by, sorry,
proxying.
can you explain what you mean
Oh,
by
let me give you more
get side?
context. Let me give you
Okay.
so much more context. This is Iroh under the with this structure. There is a provider that is a longer running provider. This isn't always this isn't every scenario that can happen, but this is just this scenario. There is a long running provider that is expected to be up and running that is serving some content, and it is behind a NAT. Then there is some node that wants to fetch that content. This node spins itself up, does all of its connection gloriousness behind its own NAT, and then requests data from that provider. So the provider in this case is called SRV, so the serve side, and then the person who's getting is the get side. Is that
Okay, so what does node mean here? Like, I guess.
Oh, sure. Oh yeah, totally. That's the weird thing. That's kind of a weird bit that comes out of the fact that this is a visualization of every packet destination, not necessarily all of the peers in the system that we're working on here. So these nodes are during our stun net check report, should we call it, or net check probe, which does stun, hairpinning, captive portal, all of that jazz. The stun, we send a UDP packet to a specific IP to figure out how our NAT is with hairpinning, and that is represented by this 203.0.113.1 node. So that's just a packet gets sent somewhere. And so that node is now that potential node is now represented in the SVG. And then this 111 node is a DNS request that we send a packet, a UDP packet, also during our setup. And that's just represents, hey, someone sent a packet here. So it's a little confusing. The actual,
but who is 203.0.113?
That's the hairpinning address. That's the address we send to. That's the address that we send to see if our NAT supports hairpinning. That's not an actual person that exists, or I don't really know what to describe it. The thing that is happening here, the SVG that this represents is a parsed log of all of the packets that get sent. So any packet that gets sent to an address, so any address that gets dialed at any point is represented in this figure. So those just happen to be two addresses that get dialed. Yeah. So it's a little confusing because they all seem to get equal weight here with the image, but the actors that we have here are or the nodes that are what you would think of as the two different peers are this server side, or serve side, I should say, provide side, and this get side. The NATs that represent them are they're supposed to be behind the NATs, and these are the two NATs, or the two representations of those NATs. And then this is the derper. So that's the proxy server.
Got it. So Kuhn has a question on how do you check if the NAT supports hairpinning?
You send a request to this address, and if, oh God, I forgot the exact protocol. You send a request to that address, and when you get a response back, if you get a response back, then you know that your NAT or your router will translate the addresses to send it back into its own local network. And if you don't get a response, then you know that NAT or that firewall or router or whatever won't translate those addresses correctly. Did that answer the
But
question? I can,
it's a specific protocol that you use to check this.
here, let me. I can, how about this? I will,
Oh, is this
at the end of the
reliable?
call, I can try and look for the exact bit here.
I'm sorry for this question, but yeah, is this reliable? Like, do routers who, so as I understand, this is dialing back to your own IP address, right? The node
Yeah.
says, yeah, ask the router to just send the packet back to itself.
Yeah.
Is this reliable in general? Like, have you seen
To-
issues? Have you seen
to
finicky
be-
routers?
To be perfectly honest with you, I don't know for sure.
Sure, okay.
Like, I don't
Yeah,
know in the
even-
wild, I don't know in the wild how much this actually ends up affecting like the rates of connections. So I actually don't know.
sure.
Yeah. I know it's a random piece of the magical NAT puzzle. And I also don't know the number of, the same way that when there's a whole section of this probe when we're trying to figure out all of the information about all the addresses we can personally be reached on. There's a whole port mapping area where we've implemented, hey, asking your router, if you support port mapping, can you please do this? But the percentage of what each router in the world actually speaks these protocols, like, we're just not totally sure about how much it actually ends up affecting things. Once we start getting this into the wild and we have metrics and things, I mean, we'll know more, but right now all of our just like dog food testing happens in these scenarios that we've spun up.
That's it. Yeah. If you ever
That
do
helps.
get some numbers, please do share.
If we get numbers, that would be like, when we get numbers, they will be everywhere. Because we like publishing our findings. So yes.
Fine.
Okay. Shall I continue with this? Any other
Please do.
questions? Okay, so let me close this. So the order that things happen right now is the serve side attempts to talk to the derper, and it does it through the NAT because the derper has a public address, so it lets it is not behind a NAT, so it's letting communication through. And what you're seeing here is like TCP. Some of it is a stun request. That the first round was a stun request. Now you're getting the TCP handshake. I'm sorry, the TLS handshake, including chatter between the derp client, which is inside the Magic Sock, and the derp server. So it's setting up its own relationship, saying, hey, I'm connected to you, keep me alive. I'm valid, I'm not a bad guy or whatever. And that's the chatter that you're seeing here. We don't currently leverage the TLS. There's a lot of stuff in TLS to make there be fewer packets that are being sent that we are not currently doing, but that is on the list of improvements. So that's all this chatter that's happening. Next, the get side is setting itself up. So it is now making stun requests, which get sent to the derper and then does its own TLS
Here's a question.
handshake with upgrades. Yep.
Why is the NAT? The NAT says Iroh serve 0, but it seems like this is the NAT for.
Yeah, those are mislabeled. Those are just mislabeled.
Okay.
Yeah. I'm sorry. I thought I'd mentioned that earlier, but I probably didn't. There's so much new information. Yeah, the NATs are just mislabeled. That's all.
Okay. Yep. That makes sense.
So one question.
Yeah.
Do they need to connect to the same derp server?
Okay, so you either need to connect to the same derp server or the same derp server or two different servers in the same derp region. which is the region is multiple derp servers that are meshed that can act as packet forwarders for each other. When you go to dial a peer, however you find out about that peer's public key or peer ID or any available addresses that it can be spoken to on, you would also, in our world, need to find out either what region is it a part of or what is its preferred derp server. And when you go to connect to that peer, you also have to dial that derp server to ensure that you can do some hole punching. Does that make any sense?
Yeah, that makes sense.
Yeah, okay. So that's just more like out of bound information that you know, and our goal is to have, or like we will eventually have servers, public servers up there that will say, hey, these are the derp regions, these are their codes. If you, hopefully in the future, if other people want to run derp servers themselves, ways for them to also be part of the region and part of the mesh network. That's sort of a later iteration of improvements that we'll make, but that is definitely on the map. Right now, in this scenario, they both happen to be, or they both know that they want to be connected to the same derp server. So then that quick packet that was just sent is, and that UDP packet is the different pings that we get. So also, okay, sorry, let me do this a little slower because this is actually where the hole punching happens. That UDP, yellow UDP packet that flew over was the disco ping message that is the get side saying, I'm trying to contact you, is just trying to punch through the NAT by directly talking to the server side. And it's accompanied by these TCP messages that are the disco messages saying, hey, try to contact me here. We got some more chatter. Let me go a little forward here. Okay, so we finally here get a message through from the derp server. It went from the get side to the derper to the server. And now the server side is sending all of those pings on all of the addresses it now knows from the get side. And then the quick connections can happen. And it has hole punched.
Wow, so cool.
Yeah, so it's a little messy in the middle there. There's also, yeah, go on.
I have a question because I would have expected the hole punch to look like get 0 going to the NAT and then going to the other NAT and then going to serve 0.
Yeah, so part of the limitations of the visualization here is that it is not an actual representation of the exact flow of packets. It's a representation of who the packets are addressed to.
Ah, okay.
When
So
they finally make it out. Yeah, so at that point, that's the point where we are able to, we actually start directly talking to those endpoints. So it's not a perfect representation by any means. The thing that part of what you end up seeing is there's a bunch of chatter between the get side going through its NAT to talk to the derper, and eventually the get side trying to connect directly to the serve side. And and then the serve side finally responding through the derper and sending its own pings. And then the magic sock is able to say, hey, we've gotten a pong back from where we know that we've gotten a good connection to this other person. Now let's just directly send to the other side. So it's not like it's definitely not a perfect representation.
Are these on the same, is the server and the getter on the same local network, or are they different local networks?
No, they're different local networks. They're different networks.
Okay. Cool.
So even though there's some weird, do you see how the IP addresses are, the local IP addresses are different? There were some weird things with our setup. The only reason that those are different is there was something odd. Oh, that's what it was. When you go to interpret the logs, anytime you would, if those two IP addresses were the same, in the logs, it would always look like the same people were getting talked to, which is why we had to explicitly give them different local addresses so that when we would interpret the logs, the logging of all the packets, we could separate who the get side and the serve side is.
Yep, that makes sense. So when the packet leaves get 0, the address is probably something like 10.0.0.4, and then the NAT maps that to the local .101. Is that right?
Yes. So no, at this point, they're actually the, sure, yes. Whatever the public address that it would have gotten from that stun, whatever is the public address that it learned from doing its stun work, that is the address that it would be. Yeah. And then I think,
So
I believe they're collated and then put it into these things. Yep. Sorry.
And you're generating this from, so I'm just trying to understand like how this red dot forms between these two things from the logs. Is it that in the logs you're like printing like, oh, .101 is sending a packet to .102?
Yes, I believe so.
Okay.
So Asmir's the one who orchestrated this, and I believe he has there's like a packet sniffer. And so anything that gets sent from any person in this system gets recorded. So any incoming or outgoing, I believe actually in this case it's all outgoing. Anything outgoing gets recorded and then collated and then put into this form.
Okay, so I guess that's the surprising bit for me, because if it was like just recording like logs of like outgoing packets, I would have expected to see like an outgoing packet to the NAT and then another outgoing packet from the NAT to the other NAT to the other node, like the getter, right?
You mean in this
Yeah,
bit
in this
right
example, in like the direct connection.
I believe that what ends up happening is any of the known actual addresses for the server for these two Iroh nodes get mapped to being the same thing. So even if, so during all of this, excuse me, during all of this dance, we yeah, you know, I understand what you're saying. Again, I could be just telling you the wrong thing.
Okay, it's
Yeah.
kind of like it's not super important. I was just curious.
Yeah, I could ask him about it. And
so Sukuna asked, when do you start sending quick packets as opposed to UDP packets? Okay,
so sometimes what happens, so the UDP packets, any UDP packet that gets sent is because, excuse me, are a couple of things. One, they're either the this hairpinning request or some DNS request that we happen to send over UDP. Excuse me. The other potential UDP packets are the disco packets that internally inside Magic Sock So all of the UDP packets that get sent are because they derive from Magic Sock putting out a non-quick packet. So like I mentioned before, either this hairpinning request or this DNS request, and also any of the disco ping, any of the disco pings that are the things that attempt to actually hole punch, those are UDP packets. It's recognized as a quick packet. The quick packets are at the start are the hand and any handshake stuff, and at this point, just the data going back and forth and getting acknowledged. Did that answer your question?
Almost. So my question is, which side will initiate the quick connection? Which side will send
In this
the client
case,
hello?
in this case, the scenario is there is a provider that's just chilling, providing, that's saying, hey, I have data here. And there is a get side that's saying, I want your data. So that get side is the one that's going to initiate the quick connection.
Okay.
Okay, I have another question about
Please.
the ping packets that you send.
Yeah, yeah.
So you said you send one ping packet to each like address that the peer reports.
Yeah.
Do you send one per interface on your side? Like, let's say you have like 3 interfaces.
Oh, I hear
Do you
you.
send one ping packet?
I'm trying to think. I think we send it, you could be.
And this is definitely a tricky question. I acknowledge that, because it's like part of the ICE spec that's extremely complicated.
Yes. And obviously we're not using the ICE protocol, we're using DERP, right? So there was a part of it that might not translate. I believe, so I'm trying to walk through it in my head. I know that we send the packets over when you create a Magic Con, you bind to a IPv4 socket, and you bind to an IPv6 socket, and all communication over that is, and then they're UDP sockets. And I believe when we send the pings, we just send them from those 2 sockets. So I don't believe that we send them over every single
I see.
interface that we know we have.
I see. So the addresses are really just like the addresses for a given interface.
You mean on the one
Well, I
who we're
guess you
sending
combine
to?
Yeah. Like your addresses, like when you figure out your addresses, they're really the addresses for like a specific interface. As opposed to like
every single
all the addresses used.
Yeah, I'll have to look into that again. That's a part that I haven't looked at in a while. Because that's one of the
subtlety
first
is
things
if
you
you
have to
bind to
implement.
0.
Yeah,
Yeah.
and it's also like literally the first thing we had to do when we did this was figure out our interfaces, and so it's like the first thing that we coded. So I don't remember a lot of it anymore.
Yeah.
But yeah, I'll have to look into that. I know that the Tailscale philosophy, they have a wonderful, so at the top of the link that I sent in the chat, here, let me get off of this. At the top of the link that I sent in the chat, there is a link to, they have a wonderful what is NAT traversal document. And they talk a little bit about how they feel that ICE is needlessly complicated, and that so they came up with this new protocol, which is the DERP protocol that we're using. So there might be some more insight there that you can gather. Yeah. Any other? I can talk about this all day because I do it all day.
I also recommend that blog post. It's very good. So for folks who haven't checked it out, please do.
So when do you decide that, okay, we can't hole punch, like it is hole punching has failed? Like,
Yeah, I
and
guess
till that
oh, go on.
point, have you like stopped transferring data from that server? Or
I'm
like
sorry,
not
can you say that
started transferring?
can you say that second question one more time?
I mean, my point here is that this is a node which wants some data from the server, right? And it has come across this node via some DHT or something, and it knows its derp address. So now it can decide to hole punch and wait before fetching the data.
We
Or
never
it
wait.
can just,
Okay, so here's
how does the switching happen? Yeah.
Yeah, okay, fabulous. Part of the philosophy, part of the reason we liked the Tailscale philosophy and we took their approach is that as soon as you have a viable connection to the other side, like let's say you know that you get communication that, hey, we actually can use the derper as a relay. This other person, this other node is connected to this derp server. We immediately start sending packets over the derp server. So there is always the fallback. So, and it's only when we get proof that we have a hole punched connection, do we upgrade and do a direct quick stream. So in the worst case, hopefully, in the worst case, you are just sending the entire thing over a relay, over an HTTPS, TCP, boring relay, slow relay. That's your worst case. Unless obviously there's some weird, you're behind some firewall that doesn't allow you to talk to anyone or whatever. We can't solve every case, but so it's actually almost like the reverse way of thinking about it. We don't hole punch first and then relay. We start sending the packets and attempt to hole punch while that's happening. And if the hole punching happens, great. If it doesn't, your relay bill is high. Like, did that answer your question, or is there some other aspect?
Yeah. So you are now basically multiplexing a stream over all possible connections to the server. Is that what you're doing? Like not using
Yes,
a quick stream?
you could say that in a way. However, we only ever send the actual data, like if you're doing a data transfer, the only data actually ever gets sent at maximum over 2 pieces, and that will quickly fall to 1 if the quick connection doesn't ever work. Like if you try to make, because we're always attempting to send over UDP as well, over every iteration, unless we have no valid addresses. Either we get proof that that quick connection works, in which case we drop all of the, excuse me, denomination, and we drop all of the, either we get proof that that quick connection works and we drop the attempts to send it over the relay, or the opposite happens and we don't get any communication over that quick stream and we just send over the relay. But essentially what you're saying is, yes, we end up multiplexing this transfer. That's definitely a way of describing it.
Yeah, that's nice. Thanks. Yeah.
It's just a different like point of view on it. I think it's like everyone's trying to do the same thing. It's just the stack ends up being in different places.
There's a draft right now on quick multipathing. And it sounds like if this ever, matures, it will be, I think, pretty interesting to a lot of people, but also to this use case, right? Where you can do a multipath over a relay and also multipath when you get the direct connection. And if that works, I mean, you probably don't even really need multipath for this use case because you could just do like the connection migration stuff. But the multipathing is interesting because you could always be ready to fall back on the relay. Like you keep that path open.
Yeah, that's true. Yeah. I'm not opposed to people taking work out of our hands. Like, do it for us and we'll take it out of our code and then I don't have to maintain it. That sounds wonderful.
Yeah, definitely.
One thing that has been kind of interesting is there are a bunch of quick implementations that are faster than the one we are currently using, which is Quinn, but we cannot use them because they don't allow us to do this hacking of the async UDP socket. So it's the only one right now that allows us to plug in your own socket. So
Right.
hopefully, although the Quinn API, people on our team seem to be fans of it over some other quick implementation APIs. I'm not the expert in that, but it might be nice if in the future either Quinn gets faster and then we just win for that, like get wins from that, or if there's another implementation that allows us to do this nonsense, we could get some wins that way. But yeah, so that's where we are now. It works. Like when we do our dog fooding, like you get them. If it's only over a relay, it's not fast, but it happens. And I think we're going to be in the like improvement game for a while. So
Yeah, it seems like there's a lot of things to like keep improving too. So it seems like yeah, there's plenty of stuff to do still.
Yeah.
I reskimmed this article, the tail scale, to answer this question about like what does it do for each interface, and I think it just does like the dumbest best thing. That's my bias here, where it just like sends a ping packet to everything on every interface, which like you might argue that like, oh, this is being wasteful and you're spamming the network, but also this is like not that many pings, right? If you have like 16 addresses and you have 16 local interfaces, like 256, that's fine. Right. But yeah, I think that's what they do.
okay, cool. Yeah, and again, I'm not sure if we've implemented it that way. It's going to be fun to clean a lot of this code up and revisit things now that I'm older and wiser.
Yeah, I would also be really curious if like mask works really good for you guys, or if it doesn't, and if it doesn't, like why also. Like I think that would be really cool. I think
There's a
mask is
ton of
how
Go on,
ahead.
sorry, go on. No.
I think mask is how like the Apple iCloud proxy works, but I could be wrong, so don't quote me on that.
Yeah, there's going to be a lot of fun, I think, research projects that get to come out of this where we can replace parts of the stack and see if they do better. And then whatever's fastest wins.
Cool.
Yeah.
Okay, so we're coming up on time. I want to where can we find you if we have more questions, if I have more questions about this, or thinking about related things?
I'm on Discord, on the #0 Discord, if any of you are there.
How do we join?
Also, you can find me at, I'll put it here, Casey at #0.computer, and I'm Ramfox on, and I think I actually am Ramfox. Like I think I got the name Ramfox. Like I don't have any little special doohickeys when they made everybody change their Discord stuff. And
Nice.
I'm Ramfox on GitHub.
Cool. Okay. How do we join the #0 Discord group?
If you would like to send me a ping on Discord,